department, and he will be giving a talk on angle defects and the polyhedral Gauss-Bonnet theorems.
Okay, well, it's a great pleasure to see the NSF funding of worthwhile causes, and to see the last throes of our Beaver grant in action. So let's see. So I want to talk about what is a really fundamental connection between topology and curvature, known as the Gauss-Bonnet theorem, but sort of at a more combinatorial, mundane level, if you will. So this is kind of like topology and curvature for, let me say, non-mathematicians. I was going to say something else, but okay, so topology. Well, what's topology? Well, let's just say it's the study of shapes up to deformation, or manifolds up to deformation, if you know what a manifold is. But more broadly, it's the school of thought that holds that an amoeba is the same thing as a round sphere, or more classically, a torus or a donut is the same thing as, let's see what I do here, a coffee cup, okay, or a two-hole torus is the same thing as the head of that guy at the coffee shop that has the big things that he Okay, so that's allowing a little roughly accurate nevertheless. And what's curvature? We sort of know what curvature is loosely. I have a chalkboard intended to remove my finger. So, what's curvature? Well, this is something straight, and this is something curved. Okay, so from the point of view of plane geometry, we have some idea of what curvature is. Some things that aren't straight. Okay. How not straight is it is the curvature. Okay? So the trouble is that things that are curved can curve in lots of different ways. Well, pretty much in the plane, at least, you're either curving to the right or you're curving to the left, or the right or the left, or whatever. Okay, so we can kind of nail this down in here. Difficulties start to appear when we consider curvature in 2 dimensions. So say for nice smooth surfaces in R3. Well then, if you're standing on the surface, you could imagine saying that it was a little curved, say if you go in that direction, or maybe it's very curved if you head it further back. Okay, so there's sort of different kinds of curvature in different directions. So Gauss was a smart guy, and he came up with a way to sort of compile all of this curvature information into a number called the Gaussian curvature. And what this ends up being is some number associated to each point on a nice smooth surface that is, if you like, the product of the maximal curvature. So you're as it turns out, and this is what I'm going to be vague about, there's always two orthogonal directions on the surface. Well, they need not be. Let's just skip the orthogonal part. Okay, so there's sort of directions of maximal curvature, and in general, these are sort of two directions that are perpendicular on the surface, and you can take numbers that you get from looking at those directions as sections, plane sections of the surface, and multiply them together to get a number. But qualitatively, you have the following sort of fact. Okay, that number is positive for the sphere, 0 for the plane, and negative for something like the hyperboloid, where, if you like, the directions that you curve away from a given point are opposite from the point of view of the tangent plane. Okay, so let me not say more about it than that, because I want to get at a more combinatorial notion. Okay, so whatever this Gauss curvature is, it's positive here, it's 0 here, and it's negative here, qualitatively. Okay. And the amazing part is that he figured out that this is something that connects in a deep way with the topology of the surface. You imagine that somehow you could take an embedding of the surface, some nice surface, and you could just pop it in this direction or that. Certainly you can change the curvature. And you can change the curvature locally, but what he learned was that actually there's always some cancellation of the curvature in a global sense. Okay? So that's the content of the Gauss-Bonnet theorem as it happens. But let me try to get at a more kind of simple-minded notion of curvature. Okay, so in the plane, here's a plane. If I'm an ant living on the plane and I drive around, and I want to get back to my house, okay, and here's my street, so I have to be pointing in the same direction because it's a one-way street. What happens as I move around here? Well, the direction I'm going changes, and the total change in the direction is 2 pi radians if I reckon the change positively as I turn to the left. Okay? Yeah.
Would you really be driving around if you were an ant?
Well, yeah, an ant. Here's my ant. Okay, so right. I mean, really the question is, would you have a chimney? So, but okay, I might take a detour and go to the ant Starbucks and get an ant cappuccino. And the interesting part is that, well, it would take me longer, and my tangent vector would sort of do some weird stuff there, but the net turning, as I go all the way around this loop, turns out to still be 2 pi. It doesn't matter what route I take, okay? So 2 pi sort of is some important number for a closed loop in the plane that encloses a region sort of to its left. So you think of it as an oriented loop. Okay? Right. So now so you might think, well, okay, what about an ant that lives on the cylinder? Okay. And now this ant is driving around the cylinder. Well, how do you tell how much you're turning? So you imagine that you've got some tangent plane. The ant doesn't really know that that the cylinder is curved, and he's just sort of driving along and checking how much he's turning to the left and to the right with respect to the tangent plane. So to demonstrate this, this is like a Google Maps for the ant, sort of colored in half. Well, we can flatten it out just by pulling the tape off and sticking it to the wall, and it was already sort of flat is the point. Well, not everyone can see this. So anyway, here it is. And you flatten it out on the wall, and well, whoops. Anyway, it's still flat. Okay? So the total turning of the Antmobile, again, on the cylinder, even though the cylinder somehow demonstrates some amount of curvature, the total turning, this is going to fail miserably, is anyway, it's 2 pi. Okay, so we sort of take this as our benchmark, 2 pi, and we say, well, okay, how does it differ from 2 pi? Okay, so if we have, so what is the defect or difference? i.e. 2 pi minus the total turning. Okay. So in this case, we would have 0 for the plane and 0 for the cylinder. All right, so what if you were ants like us, and you lived on a not totally round, but nevertheless, for all intents and purposes, mostly round sphere, and you're driving, again, oriented, so your direction is so that the region you're enclosing is always on your left. Okay? Now, what happens? So what's my total turning? Again, this is called developing. You roll the path out onto the plane. Oh, see, it always messes up the blackboard. I'll just tack it on later.
You can lower one of the screens.
Yeah, that's right. Okay, so you notice that I can't totally flatten it out, right? Or at least I've set it up that way. Okay? So as I start with my vector this way, and I drive around the path, my turning is, oh, well, it's almost, okay, so it's very close to 2 pi. Maybe it's just a round off error. Okay, so let's take this guy. We cut it and we develop it onto the plane again. So starting and then heading off. Well, okay, so that's a more significant disparity. So here the defect is like epsilon or something. Okay? Whatever epsilon is. And here I start out and I'm turning and I'm turning and I'm turning. I think I'm making a full loop, but well, from the point of view of how much I actually have to turn the ant steering wheel, okay, I'm actually only turning, I'm not turning full 2 pi, I'm turning pi. So 2 pi minus that turning is pi. Okay, so there is something qualitatively at least different about driving on the sphere. There's a question. Oh, sorry, yeah.
What happens if you drive around the cylinder all the way?
Aha, that's cheating.
That's where the Starbucks is.
That's right. Well, then you just have to keep going. You're not actually back. No. So I was making a quiet stipulation that you always enclose a region to your left. Okay. Now, the reason for that is going to remain somewhat murky. Okay, but it's a good question. Okay, so as long as I enclose a region to my left, I can calculate this defect. You do make a good point. Okay, so there's something else going on there. Okay, so now my defect is what? Well, 2 pi minus the total turning. I start out here. Well, now I don't turn at all. So the defect is 2 pi. Okay, so when you think about air travel, so here's like a 3-stop itinerary. Well, except now the region I'm enclosing is actually all of the top of the sphere by convention. So I'm traveling in this direction. What did I say? I'm traveling this direction. Well, now my total turning is actually negative. My turning is actually negative. I start out this way, turn a little bit here, turn a little bit there, but I'm turning negatively in terms of the number of radians my tangent vectors go. So I have 2 pi minus roughly pi. This one has defect 3 pi. And for the last guy, again, if we orient so that the region we're enclosing is all of this, then the defect is approaching 4 pi. Okay, so, all right, so that's a little mysterious. And is somehow ultimately different from the plane or the cylinder. Okay, so, well, let's try to sort of back up a little bit, because really even saying what this defect is a little bit fishy, right? I sort of did something with tape and used my finger. Okay, so that's not calculus or differential geometry. Okay, but things like polyhedral, okay, so there it's a little clearer what's going on. Okay, so let's take all of these solids. So we have tetrahedron, cube, octahedron, what comes next? The dodecahedron and the icosahedron. And let's look at what, well, so here now we have a slightly different notion. So here we can talk about basically all of the faces, and the joins of the faces are essentially flat. I'm driving over this thing. I don't have to turn at all, so I can just go straight, develop that straight out onto the plane. So really, everywhere it's somehow flat except for at these vertices. And we can measure the same thing. So the angle defect at a vertex is 2 pi minus the sum of the angles at that vertex. Okay, so this should be easy to calculate for these guys. So what's the angle defect for the tetrahedron? Bueller. Anyone? Pi. Okay, so here's, let's do a sort of reverse. Defect for the tetrahedron, we have pi because we unfold this vertex and we have 1, 2, 3 equilateral triangles coming in at the vertex. Okay, and this one I didn't have to work so hard to put it together, so I'm like opening it up so you can see. Whoops, there it goes. Okay, so anyway. Okay, so there's our defect at a single vertex. But now let's redo the same story. So if we're a loop going around a single vertex, then what's the defect in this? If I put a piece of blue tape going around here, what would I see as the total turning of the tape then? So how many times do I have to turn if I just go straight across? Turn once, turn twice. Okay, to connect up. Any guesses? Well, it has something to do with the defect. Yeah, right. Okay, so in fact, both the defect and the total turning are pi in this case. Because 2 pi minus pi is pi. Okay? So what if we took a different path that enclosed now, say, what do I want to do here? 2 of the vertices. So, yeah. Okay, so. Okay, so this guy comes back here. Yeah. So a path just goes straight across there, connects up to a closed loop. So what would the total turning of that be? 0. Okay, so the defect is then, well, the defect is 2 pi. Okay, so this is just the defect at a vertex, but then if you look at loops that enclose more vertices, the defects add to give you the total defect. Okay, so how about for the cube, what's the defect at a vertex? Okay, so pi over 2. You're on a roll. Octahedron. How about octahedron?
Pi over 3.
What's the vertex defect for this guy? Well, there's 4 equilateral triangles. So 2 pi minus 4 pi over 3 is 2 pi over 3. Okay, for the dodecahedron, it's a little more subtle. Okay, so anyone remember what the interior angle of the pentagon is? Yeah, Google. Okay, so what is it? Anybody? Rich, what is it?
The interior angle?
Yeah.
I think it's 3 pi over 5.
3 pi over 5, okay. So what's the defect in a vertex?
2 pi minus 9 pi over 5.
Which is?
Pi over 5.
There you go. Okay, so no tenure revocations today. So, and how about for the icosahedron? Well, pi over 3. Okay, so now if we take the total defect, which is the sum over all the vertices. Let's see, did I give this a name? So the defect at a vertex V we call kappa of V. So what's the sum of all the kappa of V's? Okay, for the tetrahedron there are 4 vertices and there are 4 pi's therefore. So I get 4 pi. For the cube, how many vertices are there? There are 8. So 8 pi over 2 is 4 pi, and so on. Okay, for the octahedron, I've got 6 vertices. Okay, 6 times 2 pi over 3, good, is 4 pi. Let me be a little more for the video camera. 6 times 2 pi over 3 is 4 pi. The dodecahedron, this is always a head scratcher. How many vertices are there here? Yeah, okay, so there are 20, right? Yeah. 20 times pi over 5, again, 4 pi. It's a good way to remember how many vertices. Okay? Or for the icosahedron, 12 times pi over 3 is 4 pi. Okay, so there's something fishy going on. So what do all these polyhedra have in common, other than that they're all polyhedra? Well, they're all topologically spheres. Okay, so let's move into the land of surfaces for a minute. So it turns out there's a nice classification of surfaces by their closed surfaces by their genus. Okay, so there's the sphere, which has genus 0. Genus is just the number of holes, the number of handles on the coffee cup, if you like. So here's the number of ears on the coffee guy. Okay, here's 2 handles, and so on. Okay, and there's, so this is a good classification, it's just by numbers. Okay, what am I saying topologically? Well, there's this thing called a homeomorphism. So, and topologists are interested in objects up to homeomorphism. Okay, so a homeomorphism is just a bicontinuous bijection. Okay, so that's basically says one shape can be sort of grafted onto another and vice versa without ripping or tearing the surface in this case. Okay, so there's another related topological invariant you may have seen called the Euler characteristic. This is also a number, and it just follows a slightly different linearly related progression. So here we have decided to take 2 for this one instead of 0. This one is 0. This one is -2. And then it's better to put in the next one. So this has genus 3, and the Euler characteristic -3. The Euler characteristic has a combinatorial definition.
-4.
Sorry. So it is the vertices, the number of vertices minus the number of edges plus the number of faces in any polygonal decomposition of S. Okay, so we put a bunch of lines and vertices and connect them up and decompose the surface into polygons, meaning that they're just disks. Okay, and we do this count, the number of vertices minus the number of edges plus the number of faces. That turns out to be an invariant, topological invariant of the surface called the Euler characteristic, and it's related to the genus by the formula chi of S sub g, the surface genus G, is equal to 2 minus 2g, that you all just pointed out. Okay. So this classical Gauss-Bonnet theorem I mentioned and I'll just state it in a special case, is the following beautiful formula that if one calculates the curvature at each point of a nice smooth surface and takes what's called the total curvature, which is kind of like this total angle defect we just talked about, over the whole surface. Okay, it's just some kind of integral over a surface, like multivariable calculus. But this is 2 pi times the Euler characteristic. Okay, so at the end of the day, what this means is that if I took this basketball and I tried to flatten out part of it, some other part of it would have to get more curved. So there's cancellation in the curvature of a smooth surface. Okay? Now, again, this is a beautiful theorem. It's something anybody can read, and it's worth reading. But one, it doesn't apply to these polyhedral surfaces because we don't have a good notion here. Well, it turns out you can define it and make it work. But this gives us, these polyhedral kinds of surfaces give us a really straightforward way to understand what's going on. Okay? So these are some polyhedral surfaces. Let me define a more general notion. The definition, polyhedral surface S is a union equal to GK of triangles, closed triangles, along your edges, satisfying the following. One, each side of each TI is identified to exactly one side of another J, and I not equal J. No two triangles have more than one side in common. Okay, and then this is sort of a technical condition. And maybe I'll state it in a technical way and then just draw a picture. So the length of each vertex of S is connected. Okay, what this means is that you don't have any vertices that serve as cut points for this surface, local cut points. And what that means is, let's say I have a picture like this with a vertex, three triangles coming into that vertex. I can't have another part of the surface just touching it at the vertex. So something like that. Okay, an hourglass type picture. So removing this vertex would disconnect the neighborhood of the vertex. And disallow it. That's what that means. So now I have, okay, and for the moment I may as well assume, I think this is just sitting in R3. Not so much. All right, well, these things have Euler characteristics that are eminently straightforward to calculate. You've already got a decomposition into triangles, so you may as well count the vertices, edges, and triangles, and then take the difference. So then chi of before polyhedral surface. Well, anyway, chi of S is equals vertices minus edges plus, we'll just call it T for the number of triangles in this space, K, in the surface. Okay, so here we go. Here's the polyhedral Gauss-Bonnet theorem. If we define the angle defect, so let kappa of B for a vertex equal 2 pi minus the sum over theta I is the angle at B. Okay, so we just get the angle sum around B. subtract it from 2 pi, well then, for a polyhedral surface, S, the total angle defect satisfies sum over the vertices kappa of V equals 2 pi times the Euler characteristic. Okay, so if you like what we've done with these polyhedral surfaces, they still have some kind of curvature to them, unless they're just flat. Okay, but the curvature is concentrated at the vertices, so the triangles themselves are flat. The edges, they meet in such a way that you can unfold 2 of them onto a plane, so along the edges, there's no curvature either. But now the curvature is all kind of nestled at these vertices. All right? Okay, so now you can channel Gauss. What would Gauss do? WWAD. Okay, so, well, what's the angle defect? Okay, so let's develop some notation. So let VI, I equals 1 to V, be the vertices, like TJ, J equals 1 to big T, triangles. Now I let theta VI TJ equal the angle of TJ at VI if VI is the vertex TJ and 0 otherwise. Okay. So how do I write down what the total angle defect is with this notation? Sum I equals 1 to big V of the angle defect. Well, each vertex, how do I calculate the angle defect? Two pi, right? So this is just V times 2 pi. What is it? How can I write this down in this notation? Well, I take 2 pi minus sum of the angles. So, okay. So what's the sum of the angles? First, I need to sum over the vertices. I equals 1 to V of 2 pi minus the sum of the angles at V. Okay, but I've conveniently chosen this notation so that I get 0 for VI TJ if TJ isn't incident on VI. So I can just take the sum over J from 1 to the number of triangles. Theta VI VJ. Okay, and that counts all of the vertices that are incident on this particular, all the triangles that are incident on this particular vertex for each I, and subtracts their angle values. Alright, well, we can count this differently. We can just say, well, this is just 2 pi times B, and ultimately what am I doing here? I'm just subtracting off the sum of all the angles. But what's another way to count the sum of all the angles in a polyhedral surface? what's the sum of the angles in one of the triangles, for example? Pi. Okay, and how many triangles are there? T. Okay, so this is just 2 pi d minus pi t. Well, that's not exactly what we were looking for. We're looking for something like 2 pi times vertices minus edges plus triangles. So right now I have 2 pi times b minus t over 2. Okay, so what now? Any bright ideas? Is there any interrelation between, say, the number of edges and the number of triangles? Three edges per triangle, indeed. And how many triangles per edge? Right. Okay. So what that means is that we can write note 3 times the number of triangles is equal to twice the number of edges in one of these polyhedral surfaces. Whoops. Negative mass blackboard. Okay, so then we can just add and subtract this quantity plus 3. Well, let's add and subtract, say, pi times this quantity. 3 pi t minus 2 pi e, and Viola. Okay, so 2 pi vertices minus edges plus triangles. So this is very simple-minded. What are the kinds of consequences that you get? I mean, just for polyhedral surfaces in R3. Well, interestingly, if all angle defects are positive, what kind of Euler characteristic can we have? We can't have 0 in particular, right? And we can't have anything negative. So then the Euler characteristic of S is equal to 2 because there's no other options. Okay, so you can't construct any other surfaces but spheres when all the angle defects are positive. Okay, and if we just forget about the requirement that the surface sits in R3 and just construct abstractly a surface out of gluing the triangles, and similarly, if all of the angle defects are negative, the only kinds of surfaces you can construct are surfaces of negative Euler characteristics, namely genus 2 through or higher surfaces. Okay, so there's Gauss-Bonnet for the rest of us. All right. Thanks.
Okay, let's